Okay, how's it going? My name's Sam, and this is the not actually live stream, pre-recorded week 8 for Gen Chem. Spring 2023, we're going to be doing all sorts of stuff with standard cell potentials. Sometimes not standard, maybe. Cell potentials for sure. So what does potential mean in this context? Potential is talking about electric potential, the units of which are volts, and ohms and amps and joules and electron volts and coulombs. It all blurs together, but we're just going to talk about volts, keep things simple. We're not going to unpack that unit right now. Um, for a cell, which is, basically like a battery, could be a battery like that, double A style, or it could be more likely in the chemistry class, a battery like this, where you have an anode over here and a cathode over here, and they're both in aqueous solution. And at the anode, oxidation occurs. And what that means is the solid metal anode loses electrons. The electrons go up here across this wire. And the atoms that lose the electrons enter the aqueous solution as ions, typically cations. There are counterexamples for sure. There's lots of variations on this, but this is pretty much what we're talking about for all these examples. We have a solid metal that loses electrons and sends them over to the cathode where the opposite happens. Here we have cations that basically get glued on to the cathode with the electrons that came off the anode. So this is where reduction happens. So that is what we're talking about when we're talking about a cell. And to calculate the standard cell potential for any of these reactions, we essentially just have to determine which of the reactants, that is to say the left side of this chemical equation here, which of the reactants is being oxidized and which is being reduced. And I believe I just underlined those in the correct order for that one. Uh, which could be phrased as which one is the anode and which one is the cathode. And the total, E cell really means E for the total cell. And that is going to equal cathode minus the anode. I don't know, one way to maybe think about it is the electron initially is at the anode and it finally is at the cathode. And we always subtract initial from final. I don't know if that's a great way to think about it, though. This is a perfectly fine thing to memorize. Now, it bears mention that in both of these cases, we are talking about the voltage potential for the reduction. There's one way to approach these problems where you convert the anode side into the oxidation, in which case you would add it instead of subtract it. Whichever way you do it, just be clear on what you're doing. I'm going to consistently do it this way because there's this table over here. This is Appendix L in the textbook. And here's some equations, by the way, also. So I kind of copy-pasted this in chunks. Table L in the Libra text, Open Chem. I always call it the wrong thing. But in the textbook, that's where you get this. And all of these are the standard potential For this being a reduction. I wrote that up here because I feel like that needs to be included. So, to answer this first question, all four parts, we have to identify what is the cathode, which is being reduced. We have to identify what is the anode, it's being oxidized. And then we go look up the reduction potentials of each of those on the table and then simply calculate it like that. And then to determine if it's spontaneous, long short, if this is positive, then it's spontaneous. There's potential for those electrons to move and do the reaction as it is written. And that's kind of ignoring what potential really means conceptually, which I may or may not succeed at explaining if I even fully get it myself. So I'm not going to really try to talk about it. I'm just going to crunch these out now that we sort of laid down some of that background. So for the first one, for A right here, the thing that starts solid and becomes an ion, right? That's what I was describing over here. The thing that starts solid and becomes an ion is manganese. And it looks like manganese, oops, N, becomes a 2+ cation, meaning it must have lost 2 electrons. So that's the oxidation. It lost electrons. It's an oxidation. That's the anode. That's going to be the second part when we put this together. That's what we're going to subtract from the part where the nickel cations, aqueous, right? Aqueous, solid, gains, oops. By gains, I mean they're like reactants. The nickel gains 2 electrons and becomes solid nickel at the cathode. Okay, that's the reduction. Gain of electrons, oil rig. Oxidation is loss of electron. Reduction is gain. So when we look at this table, the reduction part will be in the correct order because it's a table of potential for reduction. The anode part, the oxidation, will be backwards in the table, but since we're subtracting it the way we're doing it, we're just going to take the number it says. Again, you could flip it from the table and then add it here, but I'm just going to stick with one method. So we got to have manganese 2+ and nickel 2+. So I grabbed the whole table in part because I just want to illustrate that it's really easy to rush through this table and get confused. For manganese right here, it's not going to be too hard, but what if we were looking at all these manganates, right, where we've got MnO2 being reduced with just water, but over here we have it being reduced with acid, and those have different reduction potentials. This is negative, meaning it wouldn't happen. That's very positive, meaning it totally would. And then here's even more. So I just want to point out that when you're reading this table, if you are being slightly lazy, which I'm inclined to be personally, it's really easy to misread these. So in this case, the reduction of the manganese cation is not something that really wants to happen. But if the reduction doesn't want to happen, the oxidation probably does. So I'm just going to do this way. I'm going to screenshot this. So this is probably going to be, I'm guessing, a very spontaneous cell. Okay, and then let's find the nickel on here. The nickel's right here. Again, this one's not too easy to confuse, but be careful when you're grabbing this stuff. Now this is interesting because nickel really does not want to get reduced that much either. right? It's got a negative reduction potential. The potential for that to happen is negative. It's a negative potential. It's not going to happen. I'm like kind of making a pun, but I'm kind of not. That is kind of what potential is. So, those similar size. Okay. However, the negative potential of the nickel to get reduced is definitely eclipsed by the negative potential for the manganese to get reduced. So the E cell on this one is going to be, again, the cathode minus the anode. We identified that the nickel is the cathode and the manganese is the anode. So the reduction potential of the cathode, oops, a 0 in there, kind of important. And these are all in volts. Once again, that's our unit we're talking about. So negative 0.257 volts is the E of the cathode, is the reduction potential of the cathode, and that is going to be minus the reduction potential of the anode. So we can see this is going to be positive because even though we're starting negative, we're adding a much, well, I should say we're subtracting a much more negative number. Minus a negative obviously equals a positive. So ultimately we're going to end up well above 0 here. 1.18. Oops, I'm sorry. Getting ahead of myself because I'm just wondering, should I do this in my head or should I use a calculator? I'm going to use a calculator for precision and expedition. If I weren't recording a video, to be honest, I would do this in my head or by paper because I just want to retain those skills. But I'm just going to TI-80 for it here. 1.185. Okay. Yeah, so that equals a positive 0.298 volts, which is spontaneous because that's positive. If it were 0, it'd be at equilibrium. If it were negative, then the reverse reaction could be spontaneous. But if E cell is positive, then there is potential and it will happen. So once again, what we see here is that even though these two half reactions on their own, as reductions, as written here, are both unfavorable, oxidizing solid manganese is quite favorable compared to reducing nickel. And so this battery would work. If you had a manganese nickel cell or battery system, it would work. Okay, let's look at B. So it looks like, now this is something to keep in mind, that the stoichiometry does matter if you are doing the Nernst equation, because the stoichiometry, this n is going to equal the number of electrons. So the stoichiometry will influence n if you're doing these Nernst equation forms. However, for this question, we're actually going to ignore that stoichiometry to calculate the cell potential, which can be a hard pill to swallow if that annoys you after paying attention to stoichiometry for an entire year of general chemistry. I totally understand. But that is how these work. I think in a way it's because when we talk about potential, we're talking about it on the basis of a single electron at a time. So even if it took 6, as is the case here, to make this work, and I say 6 because clearly each copper is going to gain 2 electrons, and there's 3 of them, and conversely, each aluminum is going to lose 3 electrons, and there's 2 of them. So it's a 6-electron deal over here. But when we talk about the reduction potential of the cell, we're only looking at one of those at a time. When we talk about the Nernst equation, we look at all six, and then the stoichiometry matters. So I just bring that up because we're going to essentially ignore the 3 and the 2 and the 2 and the 3 here, and we're just going to make sure that when we're looking at it that we're looking at a copper 2 and an aluminum 3 because there are probably, well, actually aluminum is invariable, but I'm pretty sure there's other coppers. So aluminum 3, the reduction potential of aluminum 3 is right there. And then we've got, grab this and move it down here. Copper 2. Here we go. So this is a good example that there are 3 different copper reactions here. Oops. And it would be really easy to choose the wrong one. Now, all of them are positive, so chances are you would still get spontaneous or not correct, depending on the other half of the cell. But if you want to get a precise numerical answer that is correct, you have to make sure you choose the right one here. So again, just be careful when you're getting data off of this table or any similar table. So in this case, we're talking about this 2-electron thing. We're not ending up with copper ion anywhere in our half reaction, right? In the reaction that we're talking about, we have solid copper. So I want to choose the one with the solid copper. And that is this one right here. Okay, so speaking of solid copper, if we have solid copper, on the product side, the copper must be gaining electrons, going from aqueous to solid, right? So the copper is gaining electrons. Oil rig, reduction is gain. The copper is being reduced. So for our E cell on this one, it's the copper being reduced that goes first, and that's 0.34 volts. And, you know, there's only one way to proceed from here, but just to talk about it for a sec, we have solid aluminum here becoming aqueous aluminum here. So it must have lost electrons. And when it does, the reduction potential for each individual one of those electrons is that. Again, that's why we're ignoring the fact that there's actually 6 electrons going on and there's 3 of these and 2 of those. We're ignoring that because when we talk about the reduction potential of the cell or of the cathode or anode, it's per electron. But when we do the Nernst equation, then we have to pay attention to it. Okay, so this looks like pretty easy, and this looks like it's also going to be very positive and very happening. So yeah, 2.2. Jump the gun on the 2. 2 volts equals spontaneous. That one is going to happen. Again, so far our nickel manganese battery, it would happen. You get a little bit less electric potential out of it. This one has more. So a copper aluminum battery is maybe a better way to go. Let's bust out the next one. So here, actually, something slightly tricksy about this one. So let us note that we have and a compound ion here in this one too. And hopefully you recall that nitrate is highly soluble. So this lithium nitrate over here on the reactant side, zoom in on that a little bit for you, and this sodium nitrate on the product side will be reliably fully dissociated. So we're going to still put in solid sodium to start. And let's just bust apart the dissolved ions. There we go. And again, this is going to be dissolved in water. We're talking aqueous. All this stuff is aqueous with these cells. 3, and then we have the solid over here. So it didn't look like it at first, but let's note that there is a single mole of nitrate and a 3 on both sides. So basically cancels out. And that really makes sense because nitrate's so highly soluble and is basically a spectator ion in this scenario here. So really what we're seeing is that solid sodium looks like it's losing an electron, so it's getting oxidized. And it's fundamentally through a cable that is plugged into some sort of circuit over here that runs some sort of machine, and then goes over here, and this sodium is, here's an electron, sending this electron, or a stream of them, over to lithium. And these lithium ions are seeing all those electrons show up and thinking, hey, how about we let those electrons pull us on board and we join the growing cathode. So this cathode shrinks, and the anode shrinks, potentially till it's gone. I don't know, that probably wouldn't happen. And the cathode grows. All right, so that is what's going on inside here. So we need to just get these two half reactions where one of them is, looks like solid sodium is going to lose an electron. So again, this is the oxidation. And the other one is that aqueous lithium plus that electron from solid lithium. All right, so sodium and lithium, both of which are alkali earth metals along the left-hand flank of the periodic table, group 1. They both love getting rid of electrons. They both love being oxidized. So this will be interesting to see which one loves being oxidized more. So lithium really hates being reduced, right? Look at that. Very negative potential for lithium to be reduced. How about sodium? Not quite as negative. So let's see. Is the total cell positive or not is the question. Okay, so once again, what we are seeing in this reaction is that lithium, so I don't think this one's going to work because E cell here, standard E cell. Standard, of course, 1 atmosphere pressure, 298.15 degrees Celsius, stuff like that. So it's going to be lithium minus sodium, because we're doing the reducted cathode, we're doing the reduction of the cathode minus the reduction potential at the anode, which gets oxidized. And that's going to equal negative 3.04 volts minus negative 2.71. So, I mean, we're at negative 3, we're adding 2.71, but that is not going to take us across the finish line. The finish line being 0 here. We end up with negative 30.33 volts. That better for me to include the 0. I mean negative 0.33 volts, which equals not spontaneous. Those electrons are going to be like, no thanks, not going to flow through your circuit. I am fine over here sitting on the sodium, because even though the sodium doesn't want the electrons, the lithium wants them even less. So the way that this equation is written, with this being a reactant and this being a reactant, and that being a product and that being a product, the way it's written, it's not spontaneous. It's not going to happen. The electrons are fine. Thank you very much. Okay, looks like we have another dissolvey thing to think about. Conveniently, it's nitrate once again. So I'll try to rush this one a little faster because it's fundamentally the same. So if we sort of transmute this whole thing into how it would be written aqueously, we have Ca2 plus 2NO minus plus Ba solid barium. So solid barium, this is probably going to get oxidized, right? Because it's solid in the reactant side. And then it becomes like barium 2 plus. And clearly the calcium is being reduced because it starts aqueous. Here we go. Gains electrons. Right? It looks like this barium must lose 2 electrons. And we have a situation where the barium, this is the oxidation, the solid barium is going to lose 2 electrons and become aqueous barium cation. The reduction, the aqueous calcium cation is going to gain those 2 electrons and become solid calcium. Okay, so this will just be as simple as the reduction potential of calcium 2 plus, which is right here. Oh, and barium. I'm going to just screenshot this over here because I can fit them both in one. Okay. So for calcium, going to be negative 2.868 volts minus, so does barium hate getting electrons even more? It looks like it does. Not by much. But this is going to be a not very powerful cell, but slightly spontaneous. Those numbers are very close, but we're going to sneak above 0 here, it looks like. To positive 0.044 volts, which means it will be spontaneous. This will happen. but you might not be able to power a very energy demanding machine. So, okay, awesome. Let us proceed. So, pretty simple once you know what to look for, once you know to ignore stoichiometry as appropriate, and once you know to process the dissolving of the ions appropriately. Oh, and of course, yeah, spectator in this, spectator in that, and that should have there. Okay. So next question: determine the cell reaction and standard cell potential at standard conditions, 298 Kelvin, 25 degrees Celsius, for a half cell consisting of a silver electrode in 1 molar silver nitrate solution. Let's actually write this out. So we always go like anode solid to concentration label of anode ion, of aqueous anode ion. I don't think that's exactly the right terminology. Salt bridge. And then we're going to have cathode, aqueous cathode ion, and its concentration. Maybe the concentration should have gone on the other side. Not super important. And the cathode solid. So let's write this out just to practice doing that. So it looks like the anode part, we have zinc, then we have 1 molar zinc nitrate, and like we just did with some of the solubility things, that's going to dissolve into zinc plus and NO3 minus, and NO3 minus, you can see there's silver nitrate over here. It's just a spectator ion we're not really going to think about. I could write it in there, but the way I'm going to think about it, I'm just not. So here's our salt bridge, and then we have 1 molar, say this, it's implicit I think, but let's just put this to be good. So again, these lines are phase separations, is the point of these vertical lines right here. So if we had a cell that did not have any solids in it, which you totally can do, you can have reductions amongst ions. I don't think we're going to see any of that today, but you can. Then you would not have these vertical lines. These vertical lines are phase separations, which means solid and aqueous in this case. So over on this side, we have that silver nitrate, which is basically just going to be silver, is what we're going to call it. And then we have silver over here. So this is the cell diagram. Is it spontaneous in standard conditions? So this sounds like a Nernst equation kind of thing. And I was mentioning that we don't need to think about stoichiometry for some of these situations. In this case, if we did have to, it's real easy because it's 1 zinc. Let's see, on the product side, we have 1 zinc plus 1 silver nitrate. There we go. Leads to 1 silver and 1 zinc nitrate. Okay. Took me a sec to make sure I was doing that right. And we have that the silver got reduced, what we want, and the zinc got oxidized, which is what we want. That's what we're talking about. So these were all ones. Let me make those ones. They're not vertical lines. Those are all ones. So in this case, stoichiometry is easy, especially because what's really happening here is that the silver plus and the zinc plus, the solid zinc loses an electron, which the silver plus grabs, making it silver. And when the zinc, right, so there's an electron involved on both sides. So it's 1 electron. So N equals 1 electron for this. And that matters because I think we're about to look at the Nernst equation a little bit. And the reason I say that is because we were told that we're not necessarily at equilibrium. We have 1 mole of each. So Q, although actually now that I think about it, okay, we're going to follow through with this, but I just realized as I was saying that I'm overthinking this as usual. Okay, because check this out. Oops, not copy paste the thing I meant to. Here we go. I don't know how sensitive my mic is, but my cat is snoring on the chair behind me. I think that counts as cute. Okay. So we are going to use this Nernst equation. Copy pasted really poorly. But it's going to be real simple because Q at any time equals the concentration of products over the concentration of reactants. And, you know, if there were multiple products and reactants, then you raise them to their stoichiometric coefficients, etc. But in this case, we were told that both things are 1 molar, right? So our Q equals 1 over 1, which equals 1. And the log of 1 equals 0. Let's try it. Put it in your calculator right now. Log of 1 equals 0. I mean, I know that, but I still have to test it sometimes on the calculator. Very easy to remember, but kind of hard to wrap your head around, to be real. Very strange feature of math, in my opinion. Sometimes I feel totally comfortable with it. Sometimes I'm like, all right, if you say so. So the log of 1 is 0, meaning that we're going to have E cell times the actual reduction potential is going to be the reduction potential minus 0.0592 over 1 times 0. So, oops, that should not be an equals right there. That's just a big old minus. The reduction potential, and look, this is the point. It's not standard there. It is standard here. It's not standard here. This is the actual. This is the experimental. It's not necessarily standard. And it's going to equal E cell minus 0. That's all 0. So in this case, the reason that it's kind of important that they told us that it was 1 molar of each is because the actual reduction potential of the cell is just simply going to equal the standard reduction potential of the cell, which is just going to simply equal, as we already have been doing for these past few problems, the standard reduction potential of the cathode minus the standard reduction potential of the anode, which we just noted, right, in our cell diagram right here, that zinc is the anode, silver is at the cathode. I just said zinc is the anode and silver is at the cathode. I don't know which of those two ways to phrase it is more accurate, to be honest. I feel like they both work, but one is probably a little more correct than the other. I think I already pulled up zinc before, but let's grab it again. But what's going on here? Hang on. 2 electrons on zinc. Wait a sec. Do I have to think about that? Let me think about if I have to think about that. Zinc nitrate. I do have to think about that because it should have been zinc 2 plus the whole time. Still silver 1 plus, which means this is not 1-to-1, and I lied about all that stuff earlier. Sort of. I think it's still going to work out the same, but it's actually over here. Let's see. The thing is, Oh yeah, yeah. This is actually going to make a difference now, I think. Right? Okay. Now this is the problem with not practicing these first. Okay. Sorry, I have to go back. Just check this out. Here's why I'm tripping on my own words and process here. Is because I incorrectly rolled with the thought that zinc would be fine having a +1, but it's a +2. This is the information I have to work with, so I actually might have to change some stuff. Now, chances are, like I said, that this is going to still work out the same, but this right here is incorrect. So let me back up and fix it. And I apologize for misleading you. So that's not quite right. I'm going to back up and fix it. So we have, oh, and let me grab silver while we're at it as well. Already did silver, of course, but now we grab it again. Okay, so really going on here are zinc, starting over. We've got zinc that is solid, and it's going to become zinc nitrate aqueous, which is code for zinc 2 plus aqueous and 2 NO3 minuses that are aqueous. Okay, that's one half reaction. That's the anode. And right, this is our anode. And 2 electrons. Okay, so our other half reaction, we have silver cation, that's aqueous. And we know that it's actually going to be some sort of silver nitrate, right? Just like the zinc nitrate dissolves. We can write this up here as silver nitrate. And it's going to gain an electron and become solid silver. The thing is, we need this entire reaction over here to be doubled in order for the number of electrons to cancel out on both sides. So, let me change colors again. Therefore, it's going to be 2 silver pluses plus 2 electrons plus there's going to be 2 of those nitrates floating around. And we're adding that to the single zinc that, oh, and let's actually finish this side of it too. So for the reduction part, that leads us to solid silver. 2 of them, 2 solid silvers. And there we go. And those 2 nitrates are still hanging out. Well, I mean, with the zinc. I guess let's clean that up in a sec. So over here we have solid zinc, and it's going to fall apart. And the zinc 2 plus ions will be stabilized in solution with the nitrate. There we go. So even though this isn't lined up very nicely, actually, I'll use the magic of computers to line it up nicely. Do it like this. There we go. Now it's lined up a little more nicely. And the zinc lost 2 electrons in doing that. Okay. So again, I apologize about earlier when I said the stoichiometry is 1-to-1, because not. However, what we can see is that the 2 electrons cancel out now. 2 nitrates cancel out. So our total reaction is that our solid zinc and 2 silvers, and those come together, resulting in zinc ions and 2 solid silvers. There we go. And the whole thing was 2 electrons. So that's kind of the important part, because when we look at this table and get these values right here, this one is for 2 electrons, but this one's for 1. So when solving this system, we had to adjust it up, in this case, to 2. In a previous problem, we would have had a thing with a 3 and a 2, and it would have been 6. So we just have to pay attention to that if we're going to use the Nernst equation. However, we're still not going to use the Nernst equation. The only difference now is that this was over 2, not over 0. So there's a lot of extra legwork to say that still the E cell is going to equal the cathode minus the anode. Like I said before, I did all that extra legwork. It was probably still going to result in the same thing, and it does, but I just think it was good to go through that. It's definitely going to come up in future problems here. So we've got the cathode minus anode in this case is going to be silver minus zinc, and we're going to be reducing those in our equation here. So that is 0.7996 and minus 0.718. So this looks like it's going to totally work. And I will use my calculator. Very positive. Oops. So part of why I brought up the whole log of Q thing right now, it's going to come up in other ones, but it just illustrates that you can affect the potential. It equals E cell and standard E cell. You can affect the potential of things by changing the concentrations of the products and reactants like that. So if these weren't both 1 molar, we could have adjusted the cell potential here. But in this case, it is spontaneous. And of course, this is happening at 25 degrees Celsius was part of this question. It's happening at 298.15 Kelvin. So you have to pay attention to that. And it is spontaneous. Okay. Cool. Let's keep rolling. And sorry I'm not being super efficient. Again, I am doing these questions live for you without practicing. I prepared the sheet, but I didn't practice them. So I'm susceptible to error. I'm a fellow undergraduate after all. Okay, so write the balanced cell reaction. Here's the schema they gave us again. We've got the anode, of course, on the left, where oxidation happens. Got the cathode on the right. This is where reduction happens. Oh, interesting to note here that we're actually starting with a gas and oxidizing it to aqueous protons, hydrogen gas to aqueous protons on the anode side. And on the cathode side, we are reducing aqueous bromine, diatomic bromine, to aqueous bromide ions. So in both cases, since the actual um, reductant and oxidant, or another way to say it is the thing that gets oxidized, the thing that gets reduced is not solid, so you can't clip any wires to it, so you can't send electrons to the other part and plug a machine in the middle. But you can get around that by having a different solid piece of metal in there, a solid anode and a solid cathode with a platinum. So that's what's going on here. So the platinum doesn't really participate in the reaction. It is just an intermediary for the electron transfer. So what's going on here is that we have Br2. This is the thing that's getting reduced. It's going to get, I think it's going to need 2 electrons if we're not going to have a free radical scenario. This is one of the half reactions, the 2 Br minuses. Again, we're not worried about the stoichiometry in the cell diagram, but we are going to use it if we have the Nernst equation. So that's the reduction. The oxidation is that we have protons. Sorry, I had to do that backwards. The oxidation is that we have H2 gas that loses, we must have had 2 of them, because it's going to lose 2 electrons, and that is going to result in 2 protons. And now that I think about it, there's already 2 on H2, so sorry, we don't need the 2. They each showed up with 1, they each brought 2, so yes, this is correct now, and, let me line this up better. We're going to combine these equations because these are both happening simultaneously. 2 electrons get lost from the, 2 electrons are gained by the bromine. 2 electrons are lost by the hydrogen. That cancels. So our net equation is that Br2, aqueous bromine, and hydrogen gas. This sounds like a pretty zany experiment. Definitely do this in a fume hood, friends. This is some hopefully not fiery and explosive stuff, but this would probably get pretty feisty. Let's just say that. So that's going to lead us to 2 bromides. I should have said it was aqueous over here. And 2 protons. Okay, so those are the 2 half reactions. There is our balanced cell reaction. This is it. This is the balanced cell reaction. Turned out it took 2 electrons. Standard state conditions. Is this spontaneous? One thing about standard state is I believe we're talking about 1 molar of each, just like up here. So all this log Q stuff is going to not pertain. So all we have to really think about right now for standard state conditions, I mean, they didn't give us concentrations. The only thing that's even close to them giving us concentrations here that we could plug into the Nernst equation is that it's standard state conditions. And when I say 1 atmosphere, 25 degrees Celsius, 298 Kelvin, and other stuff, part of other stuff is 1 molar of everything. So our whole log Q here is going to equal log of 1 over 1, which equals 0. So the whole Nernst thing is going to say that our E cell can equal our E standard cell, which same deal again. E standard of the cell is going to equal E standard of the cathode minus the E standard of the anode. And room over here. I don't know. Oh man, I've been going almost an hour already. But that's cool. And I might just finish this no matter what. Do all these problems, which is a rarity, but you know, that might be what happens. So we need the bromine and hydrogen. I feel like this is going to be an easy one to maybe get confused on. Let's find out. So, okay, good. There's only one bromine to think about. It looks like bromine loves getting reduced to bromide, which totally makes sense. It's a halogen. It totally wants your electron. Bromine is so stoked to get your electron and fulfill its valence octet, right? You know what I'm talking about? Okay, so now we need this hydrogen and protons thing. That is right. Ooh, that's interesting. I guess it makes... No, wait, is that what we want? Hang on, let me think about this for a second. That's hydrogen getting reduced and becoming hydride. That's like totally not what we're talking about. Oh, I think I have to do that thing. This is what we want. I have to use this one. Oh, this was tricksy. I should have expected something tricksy. So again, I want to point out how close a call that was. I almost just took this and just rolled with it, but I'm looking for something that generates protons, right? I'm looking for hydrogen to lose a proton, sorry, to lose an electron, become a proton. I need something with protons. So, oh man, maybe this is the one. I guess I'm going to grab several of these and see. I think I have to do this one extra step here. So, alright guys, again, this is my other videos that I made when I was actually live streaming. I did practice rounds first, so I already got through any hiccups I had. Let me think about this for a sec, because we've got protons involved. I don't see any of this being for protons here. Right? So, no, there's a way to do it. It's like I have to... Let's see. You have to involve water in it, which is why I grabbed that water. Okay, one thing I'm doing right now, I'm looking for things that have... So I'm seeing things with protons. That's good. Hmm. Yeah, I think it... 0. This is it right here. Doi. Okay, this is a crucial factor, so I'm glad I just encountered that little hurdle there. And Twitch looked like it froze, but hopefully it didn't. This is the one. The reduction of hydrogen, the reduction of a proton into hydrogen is the definitional 0. It's one of these arbitrary things that we conventionally set. Because what does this really equal? Two H3O pluses are going to dissociate into two H pluses and two H2O. Now that'll be reversible, of course, but it'll happen to a significant enough extent. And then the other side of that, so basically I can rewrite this as 2H plus aqueous plus 2H2O And then this reaction arrow is going to become H2, the gas, generally. Definitely at standard conditions, plus 2H2O. There we go. And now H2O cancels out. Now we actually have the one we want. Oh, I forgot the electrons. Plus 2 electrons. Okay. So again, this is a really good illustration. If I was rushing through this on an exam and I was unprepared, or if I just didn't pay attention, it would be really easy to have accidentally used this. But this is not in this equation. We're talking about hydrogen gas, protons, and electrons. So that is actually this one, and it's 0. And that was the anode. So this one turns out to be super easy. E cell equals the standard reduction potential of bromine plus, sorry, not plus, minus standard reduction potential of a proton, basically, which equals standard reduction potential of bromine minus 0, which equals 1.0873. So as long as they're both 1 molar, that's what you're going to get from this. Volts, which equals spontaneous at standard conditions. If you wanted it not to be spontaneous, and you wanted to maintain these details otherwise, you would have to change the concentrations of things. It would probably make it not spontaneous. Alrighty, let us boldly proceed. So definitely have had some hiccups, but that's part of the process. I feel like all the hiccups have been dealt with accordingly. So our next one, get a little more room here. Ooh, so now we are stating a standard free energy change. Standard, right? So standard means that. Change is delta, free energy is that. So we're looking for the change in Gibbs free energy in standard conditions for, wait, oh, they're giving us that. I see. So they're giving us that, and they're telling us that we've got those number of electrons. I understand this. So we're going to use, what is it? N, F, E. Pretty sure that's correct, and I'm going to double check. Over in our equations. Yes, here we go. Oh, nice. I did miss a thing. I forgot the negative. Okay. Classic. I always forget little things like the negative. Negative. So the only question is, what is F? And I don't know why I do my F like that when I'm doing math stuff. I just like doing my F like that. All swoopy and stuff. That equals Faraday's constant. And like any constant, there are some permutations on what that might be, but I'm gonna meant to already have access to this. Off the top of my head, it's like 48.65 joules per coulomb, maybe mole or something. I'm gonna just like not guess that and get the actual number. So sorry, 1 moment. Do a little bit of the old one. If you are following along, hopefully you already have that. Faraday's constant. So don't get it confused with a Faraday. A Faraday is a unit, and that is not the same thing as Faraday's constant. Where is Faraday's constant? That's not it. Sorry, everybody. The thing that I'm seeing does not seem right to me. Oh, there we go. That explains it. Am I getting this right now? Coulombs. Sorry. In kilojoules. Is this the one I want? Okay. We're going to roll with this one. So I kind of had it close-ish, but apparently a little jumbled. Now, I might in a sec go double check, because I could have sworn that there was a correct version of this that... Actually, I am. If you, like, have a quick... If you want to take a quick stretch break, I say do it, because I want to double check what I'm about to tell you. Because I could have sworn that one of the versions of Faraday, with I believe the kind of units that we want, was the thing I was thinking, but I totally might be wrong. I'm totally wrong. I just apologize. I just double checked it. I was remembering the correct units, sorry, the correct digits in the wrong order, and I was overconfident. So I really apologize about that. We're going to use this one, 96485. I think I had those digits in the wrong order. Coulombs per mole. Okay. And what we're going to do is I guess we're going to solve for E cell, right? Because we're asked to calculate a corresponding standard cell potential. So we really just have to solve for E cell. So I apologize again about being confused for a sec there. We now have everything we need. We're told that delta G equals 12 kilojoules per mole. Our standard delta G, which is going to equal negative 2 electrons times 96, sorry, 485 coulombs per mole. And what is it? It's like a coulomb, a volt equals a joule per coulomb. Confirm that too, because we're actually going to need that. Volt equals joule per coulomb. Yeah? That's correct. Okay, we're going to need that. Times E cell. Because we have coulombs per mole, we have kilojoules per mole. This is going to be in volts, and we're going to convert it all using this conversion factor. So I'm going to actually just put my kilojoules into joules right now. So 12,000 joules per mole divided by -2 times 96485 coulombs per mole. And here's our per mole cancels out. And here's our joules per coulomb, which is going to be replaceable with volts, but that's going to equal our E cell. So -2 times 96485 is negative 192970. We have 12,000 joules over negative coulombs. And again, joules per coulomb, read as a C, but it's coulomb. Yeah. Equals negative 0.0621 blah 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 volts, because again joules per coulomb equals volts. So the E cell for this first one is that, which by the way, standard E cell for that one, this, and it's not spontaneous. Okay, so for our next one, I think we are going to be spontaneous because look, it makes sense. A positive delta G, as was the case in A right here, means that you have to put in 12 kilojoules per mole to make this happen. Whereas for B here, we're probably going to have spontaneous because you can actually get 45 kilojoules per mole of energy when this happens. So let's check that out. And n equals 1, so that makes it really easy. Let's just actually just line this up algebraically. I'll just in orange to make it look different. We just line this up algebraically. What was it? Negative 45. So we've got basically our delta G divided by NF going to equal E cell. So in this case, that's going to be 45, negative 45,000 joules per mole. Our N equals 1, we were told. Our Faraday's is the same. Our unit deal is the same. And, oh, negative. So negative over negative is going to be positive. 4,500 divided by 0.466 volts equals the E cell standard equals spontaneous. Whatever that scenario is, it will give you a viable battery that will provide you with some flow of electrons. Okay, cool. We're getting there, getting further and further here. So, oh, that is with that, I see. Okay. Determine this, so we're on, sorry, I'm just trying to make more space here. No, I don't want help. Oops. File, back. Oops. Come on here. Here we go. Oh, draw. Here we go. So in this one, looks like we got this mercury, sulfur, silver situation. Very interesting. So they've given us a balanced reaction here in A. So I'm going to just make sure I understand what's going on and write out a cell diagram. Looks like we have solid silver, some sort of solid mercury sulfide, interesting, with liquid mercury, and these sulfides, and we have, okay, silver cation. So this I know for sure. This is obvious. Silver cation is becoming silver. So this is our cathode for this. Is that two silvers, and it must be two electrons because silver is a +1, becomes that. So that's our cathode. And I think we already have this, like, where, right here, like right right here, 0.7996. Already got that. So the standard reduction for silver plus 1 electron becomes silver is 0.7996 volts. That's the cathode of our situation. Our anode it looks like is essentially the reduction to hydrogen. So let's see. I'm kind of like a little bit hesitant to say if that's a mercury or sulfur thing. So I'm going to look at both on this table, see what the table tells us. Okay, so here we have diatomic mercury. So this is an interesting one because look at these three different mercury options we have. Oh, and there's more? Here we go. Good. I was about to think about this too hard, but I just want to point out this is another case where look, we have 1, 2, 3, 4, 5, 6, 7, 8 different entries involving mercury. If you're not careful, it'd be really easy to get this backwards. Okay, but we found one that is exactly what's been prescribed here, so got that. Let me just bring silver back since we're doing it again. Where are you at, silver? Sorry, I skipped. There it is. So again, just noted, silver is the cathode. That means this mercury sulfide must be the anode. And first we're going to determine the standard cell potential, right? Which once again, cathode minus anode is just going to be the standard potential of the cathode minus the standard potential, reduction potential of the anode. So E cell is going to equal 0.7996 volts minus negative 0.7. This one I can do in my head. Going to equal 1.4996 volts, which equals spontaneous. Well, caveat, spontaneous if we were at 1 molar, but we're not necessarily at 1 molar. Well, we're not. We're literally not at 1 molar. It says right here that we actually have 0.1 molar of one of those and 0.25 molar of the other one. So we're actually going to see. This is going to be exciting. So in all those other examples so far, the stuff's been 1. But now we're going to use this. Our actual E cell. Well, sorry. This does mean 1 molar. So the standard E cell is that. But the actual E cell is going to be our standard minus RTNF plus the log of Q. Now, if we're at standard temperature and pressure, R is a constant, F is a constant, and T in this case is at our standard temperature and pressure. So that's where it comes from to say that E cell minus 0.0058. Is that right? Let me double check my number on this. 592. So I'll go back and fix that. So it's the fact that this equals this that makes it work. This also could go that way if you want to use natural log instead of log. I like log better for whatever reason. So we're going to use the log version. I think it often is simpler to do this. So 0.0592 log Q. Okay. over still the number of electrons matters, volts, plus the log of the concentration, the log of the ratio of the concentration of our product over our reactant. So now I guess that's the only question, is what are we going to call the product here, and what do we call the reactant? So the concentration of our reactant must be our silver. That's the thing that has a concentration because it's aqueous. The product is getting, is this right? No reduction? Let me think about it. The silver's definitely, yeah, that's getting, oh wait, are they both getting? Hang on, this is super confusing me. It looks like the way this is written, they're both getting reduced. But how could that be? Because we're going from, I think this is part of the problem. Now that I think about it, no, because this is the liquid right there. So we have that. We have the liquid on the other side. Because when that gets reduced, it becomes the liquid. So this is the oxidation. So never mind, we're good. And the thing that has a concentration is this, which is what they tell us right there. Okay. So when we write this in terms of a redox, this is what it is. Sorry, guys. Again, I'm working through this live before you. Okay, so the reason I was a little confused is because I hadn't really written out the anode equation yet. It's backwards of what's written here, I believe. At the anode, what we have is, so this must all be like in one thing. I don't know how this battery would. What we have over here at the anode is that it's losing 2 electrons one way or another. And when it loses 2 electrons, it becomes this mercury sulfide, solid mercury sulfide. Now, this is weird because usually if it becomes solid, it got reduced. But in this case, it actually was more electron rich as liquid mercury. So you can see that the sulfur lost those 2 electrons. That's what happened. So the sulfur is a reactant. Ooh, but so is the silver. Ooh, that's interesting. Yeah, both of our aqueous things are reactants. So really our Q is going to equal, do we have anything aqueous on our product side? Kind of don't. I don't know what to do about that. Because, they're basically just one. So I think we're going to have to call, here's what we're going to have to do, is the concentration of a liquid, it's kind of paradoxical, but it fundamentally equals 1. We're really talking about activity. Concentration of a solid, the activity fundamentally equals 1. So I think what we have to do is say that our products are all just 1, because our products are all solids. A reactant here is a liquid, so that's 1. These two are reactants, so we're really going to have these 2 concentrations were given. 1 for the silver and 1 for the sulfide. And that's going to be 0.25 molar times 0.1 molar. So it's going to equal 1 times 0.025, which is going to be a very big number, I believe. Yeah, it's going to equal 40. So let's see. So I think we're looking at a not spontaneous thing, right? Because this was like 1 over 0.025. That's going to equal, and it looks like we're talking about a 2-electron scenario here, right? We have 1.4996, that's this, as was solved here, minus 0.0592 over 2, plus the log of 40, which is going to equal, because 40 is what 1 divided by 0.025 equals. The log of 40, we're going to have, this should all be like, what? Right? Pretty sure that should all be like that. Check. That actually could matter. Yeah, that's all. Oh, it's times. Oh my gosh, that would have been bad. Guys, I apologize. Caught it before it was too late. I'm sorry, that's just times. Not plus, that's times. That's times. There we go. That's why. There we go. Okay. So the log of 40 is 1. 0. Log of 40 is 1.6. 0.0592 divided by 2 is 0.296. 0.0. Oops. That's what the log of 40 is. That's what 0.592 divided by 2 is. Multiply those together. We have 1.4996 minus 0.0474. And that, of course, actually does look like it's totes going to be spontaneous after all. So the actual E cell in these not standard conditions, because we have those weird concentrations, 1.4522 volts. So yes, it's still spontaneous, but a little bit less. With those concentrations, it's a little bit less spontaneous. I mean, that's like not really a very sensible thing to say, because you either are spontaneous or not, but it's less powerful than it would have been if it were at 1 molar of both of those things. Okay, cool. Geez, this is going to turn into like a 2-hour thing, but you know, so be it. Anyone who watches the whole thing gets a prize of some sort. You can prove that you did. Okay. Part B. The cell made from an anode half cell consisting of aluminum. Oh, well, it's the same thing. They're just telling us this differently. Okay. And I might just call it a day after this one. A couple more I haven't quite done yet, but those might be circle back and do later. It's like, who's really going to watch this whole video? Again, if you do, prize for you. I don't know what the prize is yet, but prize for you. Okay, so this one says a cell made from an anode half cell consisting of an aluminum electrode and a nickel electrode. Let me just try to write this out. So the anode half cell got aluminum, and we have 0.015 molar aluminum nitrate. A 3-electron solution. That's what's going on over there. This is going to prove to be a spectator ion shortly. Salt bridge. Nickel 2 nitrate. Interesting. Very interesting because we have 0.25 molar nickel 2 nitrate. So that side of it is going to be like nickel. I need more room here. I'm getting crowded with my previous answer, so let's just move all this down. Okay. Nickel 2 plus 2NO minus plus 2 electrons would equal nickel. But the problem is, first off, I should have written that backwards because this is the anode, right? Here we go, right? Oh no, I'm sorry, that is the cathode. So that was the correct part. That's the cathode. Ah, where'd you go? Oops. Solid nickel cathode. So the anode part is this. Okay, there we go. Left the L behind. So. Okay, so thing is, we do not have the same number of electrons, nor nitrates, but we will in a sec. So yeah, let me say this. We haven't canceled out our nitrates yet. That was premature. Going to, but okay. What we have to do is multiply this by 2 and this by 3 in order to get, let's do this in green. We're going to get 6 nickel 2 plus 6 NO3 minus, sorry, 3 nickel 2 plus 6 NO3 minus plus, this is the crucial part, 6 electrons is going to lead to 3 is what I meant, 3 solid nickels plus 2, oh, sorry, that 2, I added this over here, 2 aluminums. There we go. Aluminum cations, there we go. 6 nitrates plus mess. I think I am going to call it a day after this one. I had a midterm this morning. I only got like 4 hours of sleep, and I can tell I am running on fumes right now. Slash copious amounts of coffee, obviously. Okay. I think I'm doing stuff correctly. I'm just not doing it efficiently. So now we have matching electrons, so we can cancel those out. And when it comes down to it, N is now going to equal 6, right? Because N is the number of electrons that were involved in the balanced chemical equation. Otherwise, we can ignore the stoichiometry basically from there on out. Like we have 6 nitrates, those cancel, and there we go. Okay, so on the cathode side, the nickel goes to solid nickel. Okay, cool. So our standard cell is going to equal standard for nickel minus the standard for aluminum. Okay. Okay, so our E cell then, our standard E cell, is going to be negative 0.257 minus negative 1.662 equals so if we had 1 molar of each, then it would definitely be good to go. Let's see here. For our Q, it's going to be products over reactants, and it looks like our product ion is the aluminum. This one's more straightforward than the last one, thankfully, in terms of we just have clearly one ion to worry about. Our O and our Q, we need to think about stoichiometry. Did I fail to do that over here? You know, I did. I should have had a. I apologize. I should have had this be squared because it was two of those. And if I'd had that be squared, then it would have actually been 0.625. That would have been 160. And the log of 160 is actually quite a bit more. So that would have been the log of 160. So again, I apologize. That would have been 2.204. Which would have been, still would not have made much of a difference. And that's a 6 and a 5. We're taking a little bit more away, 2 more away. So it'd be more like 3, something like that. So it would have been a little less. So it wasn't a grievous error, but it was a procedural error. I should incorporate that. So this is another place where the stoichiometry matters. It matters in the number of electrons, and it matters in our mass action expression, aka Q. So over here, we're going to have the product ion, 2 plus, for that concentration cubed. So we are given that the aluminum is 0.015 molar, and these units end up getting canceled out by convention. We could take an extra step to do that, but we're just going to not. Oops, 25 cubed. Okay, so 0.015 squared equals 2.25 times 10 to the minus fourth, and 0.25 cubed equals 1.56 times 10 minus second. When you divide those, that is going to equal that's our Q. Does that make sense? Yeah, that makes sense. It's less than 1. This is not product favoring, as it's, or the products are not uh, abundantly represented right now. So that's our Q. Okay, and that's our E cell. So the actual E is going to be our standard E minus over 6 times the log of Q, which is, we just found, 0.0144. So that's Faraday's over, or the 0.0592 divided by 6 is that. The log base 10 of that is, the log base 10 of 0.0144 is negative 1.841, blah, blah, blah. Multiply those together, that's a volts. We have that it's 1.405 minus negative 0.018 blah. So it looks like this will still be positive. Got 1.405 basically minus that going to equal 1.423 is the cell potential with those concentrations. Okay, I'm going to call it a day for now because it's, I mean, we would round this up to 2 hours. I'm at 1 hour and 40 minutes. There were a couple of, there's like 4 things I didn't get to. So maybe I'll get to those later. It's more of the same of what we've been doing. Probably with a few more hurdles and hoops. So main thing is just be really careful with your table. Obviously, I made mistakes as I went, but I think I caught most of them. But hopefully, there weren't any that I didn't catch. Thanks for watching. I hope your spring term is going well, or your whenever term, because who knows when you're watching this. And always write your units, and have a good one. See you later.